Recording. Yes. Okay. So this is my MSc thesis, and the topic is degenerations of quiver representations. We will obviously define these things, degenerations and quivers, and yeah. So first of all, what is the basic setting? We will have a field K, which is we are going to assume it's algebraically closed. We'll need it all the time, and characteristic 0 also. And A will always stand for a finite dimensional K algebra, which means as a vector space, we are saying is finite dimensional over K. And by this mod D K, so on, this will be the collection of all D dimensional, now again as vector space dimension, left A modules. Okay? And so that's the basic outline. Now, what we will do just as a very broad picture, just one second. Yes. So first we'll put a affine variety structure on this set, on the set of all modules. So every module will become a point in that affine variety, in that affine space, in that big affine space. And so, second, yes. And then we will describe a natural GLDK action, this general linear group of d by d action on mod dk, some kind of a conjugation action. And so that the orbits will correspond to isomorphism classes, we'll say those things. Okay. And then basically the question will be, when is a module n, which is just a point in this big affine space, okay, in the closure of the orbit of another m, of another module m. Okay. So first we will outline a proof of a necessary algebraic criteria. So when this happens, then what algebraically, what does it imply? And that will be this, that basically the dimension of the homomorphisms from U to M will be less than or equal to the dimension of homomorphisms from U to N. Okay. So this is a necessary algebraic condition that we would outline a proof of. But then the key question will be, when is this sufficient? Okay. So when does this condition imply that the orbit of M contains N in the closure, in its closure? Okay. That will be the key question. And we will present a proof of this, that fact that it is sufficient in the case of certain algebras. Okay. We will describe. And the key difference make the tool that we will use, which is used in the paper of Reitman, which is essentially what I'm presenting, is the Ostrander-Rayton theory, which is used at in various places throughout the proof. Okay. And so this is just orbit closure problems arise in different places, but we are focusing on degeneration of modules. Degeneration of algebras is another place where this is also there, but yeah. Now, how is this presentation organized? So there are several subtopics, but we will only have like not much time. So we will only focus on the key ones, but all of them are sort of needed to understand the proof. But yeah, first we will begin with just the basic definitions and facts related to algebraic groups. Okay. And then their actions on affine varieties. Okay. And then we will describe how to make this construction of this, how to view these d-dimensional modules as affine space, state the problem of degeneration, and basically just, and this also will first give, also going to give an example of this case. So we'll take a certain kind of a certain finite type algebra, and we will take certain some n-dimensional modules over it, and we will see, we'll try to give an exact condition under which degeneration happens. So we will say that example and just outline a proof of how that happens. And then we will have to build the basic definitions and results in theory of quivers and path algebras. And then also, maybe we can just mention what work has been done so far in going from this algebraic condition that we mentioned to this geometric thing of degeneration. Okay? But then after that, we will just have to, because we will be working with these things, so orbits, how to like maybe just mention the formulas for computing dimension of orbits, conditions under which some orbit, or rather some module becomes semi-simple, what is the nature of its orbit under which it becomes, and then the key thing is, how do you actually get to degenerations algebraic, a classical condition which we will state, which we will again use later on. Okay? And then again, this Ostrander-Rayton theory is, we will again outline the steps and just mention the existence of these almost split sequences, the key building blocks of the many sequences which we will construct to finally imply degeneration. But we will only do it in the representation finite case, which is much simpler than the general case. Okay, nice. So this is one, and then there are applications of Ostrander-Rayton theory which we will use in the proofs, which is how to determine a module up to isomorphism using homomorphisms to it. And then again, this will be another important thing in the proof, that is basically we would like to see the collection of all indecomposables over a representation finite algebra in terms of a graph, and then arrows which will help us maybe capture all the basically the entire ind category of that. And that for that we will need the knitting algorithm, which again is an application of Ostrander-Rayton theory. And this again will be useful because then we would know what is the nature of the maps, and we'll then be able to construct the exact sequences to imply degeneration. And then after that, the final thing that this Hom order, which is the algebraic condition we mentioned at the beginning, when does this imply degeneration order, which will again be broken into 2 steps. So that we will be seeing. So so far, any questions? So we are, how much time have I taken? Okay, so this one will just very quickly just mention a few things. So why do we need algebraic groups? Because we are going to study this action of an algebraic group on a representation space and the definition. So this is fine. And the example, and this GLN is example, closed subgroups of that. And these are all the examples. And basically the actions that we'll be considering are regular actions. So maybe the rational representation, let me not mention so much here. But the key thing that we will need, which we'll use, is that the G orbit is locally closed. So it's constructible because the image of a it's a image of a closed set, so it's constructible, but it's also locally closed that can be shown. Okay. Now, the key thing is the finite dimensional algebras. So we know the definition, and just to say that it's not necessarily commutative. Okay. An example is this lower triangular matrices, and these kind of examples are also there. Okay. But why did I mention these kind of examples? So they have this certain nature that some entries are free and others are zero, and they respect some sort of a poster structure. But the main thing is that these also arise as path algebras. So path algebras, certain kinds of path algebras can be written in this way. Okay? But that's fine. Now, a very important ideal that we will need to work with is the Jacobson ideal. So the definitions, we know equivalence, but the key thing again here is that in the finite dimensional case, it is same as the equivalence of two-sided ideals. And the Jacobson radical is again going to be important. So we will see, and we will generalize this in the notion of categories when we define morphisms, ideas of morphisms in categories. So it's going to be needed there. And then some properties of it, which are used in computations, but maybe let me not just I'll mention a few. This that if you take the lower triangular matrices, then which is the Jacobson radical, where you just put zeros on the diagonal, everything remains same. And so let me not say this. Yeah. Now, the main problem, how do we set it up? Like I said, it's a variety, and the collection of all d-dimensional modules becomes a variety. How does it become so? So to describe that construction. So to begin with, if you have one d-dimensional module, a module, then it is 1 minute. Yeah. Then it is just to begin with, there's the underlying vector space structure, d-dimensional vector space structure. And then basically there are, so once you fix a basis for this vector, then basically, so every element of A or every generator of A gives an endomorphism, and so you get a D by D matrix. So it's basically just a tuple of D by D matrices indexed by any generating set. Okay, but the generating set we will be considering is a special one, which will take the basis, the K basis of A, and using that obviously generates it as an algebra, and then we get a presentation. Obviously, any generating set would give you a finite presentation, but we take this particular basis, and with that we make this presentation. So alpha I, alpha j, now because alpha is the basis, so you can write it like this, and all relations can be generated from here. That is easy to prove. And yeah, now the endomorphisms which are given by this action of A on M will have to satisfy these relations, right? Because they are the elements of the algebra which act on the underlying vector space of, and these are all the things that they have to satisfy. And so basically, if we denote the endomorphisms corresponding to alpha I on M as Mi, then these are the relations that the Mi's have to satisfy. And so all the information of the module is in this n tuple of matrices. And so basically any n tuple of matrices that satisfies these relations is a d-dimensional A module. Okay? And so that's how it becomes an affine variety in this huge space ND square, because I mean d square variables in every matrix, and we have n matrices because n is the basis. There will be many more equations, but that's not important now. And we will now denote this like this. So there are two notations for the same thing, but just usually this is, when you see it as a variety, then you denote it like this. So it doesn't matter. Yeah. Now, we come to this isomorphism thing. So first the homomorphism. So if you take a homomorphism from M to N, now M and N are those A modules, then basically what you get is a matrix. Once you fix a basis for things, where you get a matrix G, and this G has to satisfy this for every. So basically G of A of any X is A of G of X, but the action of A is Mi on M and it's Ni on that. And so this kind of commuting, not commuting, but kind of commuting relation is needed. And so when you want an isomorphism, then it basically becomes this. You take this n tuple of matrices and then you conjugate it. And this conjugated tuple is isomorphic, and it's obviously even only. So this is the thing. So what we basically finally get is this action that we define by this conjugation. The orbits under this action on this set of, on this collection of all modules, the orbits correspond to the isomorphism classes. This is the important fact. Yeah. So this fine. Now the main definition of degenerations is, again, if you have two these things, then X degenerates to Y if Y is in the orbit closure of X. So now these are part of a topological space, so this makes sense. And but we take Zariski closure, but then we know that this OX is in fact a locally closed set, so it's constructible. So Zariski closure and analytic closure are the same, but we mentioned to begin with it is a Zariski closure. Yeah. So we have this classical necessary condition. So when Y is in the closure of the orbit of X, then this classical necessary condition, which I mentioned at the beginning, this is true. And we also denote this by saying that X is less than Y, less than equal to Y in the Hom order. This is called partial order. And well, it's intuitive, but anyways, yeah. But the main question is when is it sufficient? So that's the main question. Now we'll give an example just to understand this. To say. Okay. So the example is that of nilpotent KT modules, but we have to say it in the setting that we have set. So what's the algebra that you begin with? The algebra is Kx modulo X to the power D. And what will be this mod NAK? This thing here we have the here. So here these are n-dimensional modules. The algebra has the D, so maybe not very good notation, but in the way we have said so far, there are two generators, the one and the, I mean, as a basis, the one and the n, the others are fine. So this is the thing. And so basically n to the D is 0. So basically these are nilpotent matrices with order at most D. Okay. So when is Y in the orbit closure of X? So now we know that, I mean, every orbit, that is every conjugacy class. So orbit become conjugacy classes. That's gives rise to a unique partition because there's only one eigenvalue. And well, there's a fact that if there are two partitions Px and Py corresponding to X and Y, and if Px majorizes Py, so majorization just means that the first part is bigger than the second part. The first part or the first partition P1 is bigger than Q1 second partition, and the sum of the first two parts is bigger than sum of the first two parts of the other, and so on. And also they can be said in terms of Young tableau box droppings from the end and so on. That implies this degeneration. This is not difficult to prove using one parameter subgroups and some things. Yeah, but the key thing is now that the converse is also true. Okay, that if X degenerates to Y, then this partition of X majorizes the partition of Y. So in this case, we have a complete characterization. Okay? And again, this is not trivial, but the idea is that first we notice that this majorization order is the same thing as saying that rank of X to the I is same as, sorry, is at least rank of Y to the I. For any I, this can be proved, it's easy. And also this thing that if X degenerates to Y, then for example, X square will degenerate to Y square. This is another fact that can be proved. Yeah. So then from this two, we basically, the last thing that we can prove is if X degenerates to Y, then the rank of X is at least the rank of Y. And then for all I, it will just follow. Right? And then we get this order in the partition. Right? So the last thing to show is, in general, what we can show is like if you have a constant rank matrices. So the conjugacy classes, all the matrices are of the same rank, right? So when you take a limit point, then it analytic limit point, which as I said earlier is same as the Zariski limit point, then its rank cannot be larger. And this can be proved using some singular value decomposition thing, but maybe I won't say the details now. If someone asks, I can try to say a little bit. Okay. So this is thing, and maybe this section I can skip because we don't have time. So I thought I would say a little bit, but how it appears in GIT and so on, and also some other places, but maybe I'll skip it. Yeah, but this one condition again, which is needed, is that if you are looking at a, I mean, if you're looking at a limit point which has a closed orbit, then it can be reached via one parameter subgroups. That is what roughly this Hilbert-Bummer criteria is saying. And the other situation I can skip. Yeah. And then we can come to quivers and representations. So, right now, so let's come here. So the definition of quivers, we know. So it's just a graph to begin with. It has a function which returns heads and tail of the arrows. And representation of a quiver, basically at each vertex you put vector spaces, and then you take maps, which are denoted by this VA from the tail to the head of every arrow. And yeah, as an example, you can take a point and we can take a double loop, and that's a quiver. And then the representation, we can take CN as a vector space, and we can take this as the, so this is just the Jordan block, single Jordan block with only zeros, is the zero is the only eigenvalue. And then we can take its conjugate, and that will form the representation. And it is a simple representation. And basically this shows that you can have simple representations of arbitrary large dimensions. Obviously it's not a finite dimensional algebra, but that's what this says. So yeah, anyways, so that's that. And so, and this sub representations in decomposable, so I'm not defining these things. These are naturally defined as one would expect. So these things are there. And then morphism. Okay, so basically morphism would here mean that from each VI you want to go to WI. So from V and W two representations at each vertex, you have a morphism from VI to WI, but they should also carry the map VA to WA, and basically that's that commuting relation. Okay? So that's, see, and from here, from there, from this definition, one can prove that, for example, this. So this representation, which is again it's a useful, it's a good, it's important representation for this representation can be normalized some sense to this representation. These are the same representations by that definition. Yeah? So this is a simpler class, a simpler member in that class. Yeah? Now these representations are defined in a combinatorial like at each where you put, but then we would want to make it as want to say it in terms of an algebra. So we make an algebra for quivers so that the representations become the representations of that algebra. And so that's your path algebras. And it's just a natural thing. You have the basically take a graph and you take the algebra generated by that graph in the natural way. Okay? So we have the natural generators are the edges and the vertices, and then the natural relation. Okay, that is just a path concatenation. And if you cannot concatenate, then it is zero. So maybe that is say. Yeah, and then one notices, and this is an important decomposition. So one notices that EI, these EIs that we have, so EI is for every vertex in Q naught. So for every vertex, they form a complete set of primitive. Primitive is important, orthogonal idempotents, and so they give rise to a decomposition of the algebra as left CQ modules. Okay, and the CQEX is just paths from X. So that's an important decomposition. And then acyclicity is same as finite dimensionalness, and a small example. And yeah, this important
primitive just means it's not the sum of two more things, no?
Sorry, sir.
Primitive just means that you cannot write it as a sum of more, right? Is that the definition?
Yes, sir. Yeah. So primitive means that EI is primitive. So EI will not be sum of two other idempotents.
Yeah. Okay.
And that basically leads to indecomposability of this CQEX. Yeah.
Oh.
Or usually the indecomposability is proved first, and then that proves. But yeah. Right. So yeah. Okay. Yeah. And then this fact again is easy to prove, but because we don't have time. So modules over CQ. Yeah, if you take modules over this path algebra, are the same as representations of Q. Okay, these are, and it's a categorical thing, same. Okay. So I have written, but let me not go in the explanation. These are treated with the same things. So basically, if you have the representation, then you have the vector spaces, you sum the vector spaces, and then the arrows that for which you had the maps, they just become the action of the in the path algebra, the corresponding path algebra. Okay, so that's the thing. And then the very important ideals for us are the admissible ideals. Okay, and the admissible ideals are described as those ideals which so they don't contain the single arrows, so they have to be contained inside. So the arrows must be of length at least 2, but then finally they should be containing CQ plus to the power, and CQ plus is just the two-sided ideal that is generated by all the arrows. So that is the definition. Now, this is the reasons why this is a good, but this is the definition we take for now. And one can see that CQ mod I is finite dimensional. Okay, so that is easy. And why I mentioned, because we are going to prove this degeneration from this algebraic condition for these kind of algebras, or maybe I should say cancellation of degenerations we are going to prove for this kind of algebras. The other step we're going to prove for general finite representation type algebras. So these are important ideas. And there are some interesting things about the CQ plus, but let me not say it now. Okay. Some facts we will need, because sometimes it's easier to work with projectives and injectives and so on. And so this is so M star is a vector space dual, is an A opposite module if M is an A module, and these categories are dual. So it basically just means there's a contravariant functors in both directions, so that the composition is an equivalence. And so that is, let me say like that. And now we'll need the CRUL. Now this again we will need in the main proof as well, and it's important in the theory, but we'll need it in the main proof as well, because we're going to make some assumptions about X and Y later. So we'll need this, and this is the CRUL theorem, that basically the unique decomposition into indecomposables up to permutations and so on. So, and the idea, but let me not say that now. Okay. Now, the two important kinds of ideas which we are going to use to build our AR quiver and everything so on is the projectives and the injectives. Not giving the definition, but in the case of in the case of path algebras, they have a very simple description. They're indexed by the vertices. Okay, so that, and also the action is combinatorial. The action of CQ is kind of like path extension concatenation and for injectives it's different, but it's a combinatorial thing, and that's again useful. And these things allow us to guess analogous results for general finite algebras, but we not to that. Yeah. And yeah, the projectives are basically the CQEX, and these are indecomposed. These are all this can be improved, but let me not go into that. Injectives, that the definition is that, I'm just giving the definition for this here, that if there is any injection, so there should be an injection from M to I, then it becomes a direct summand. So any injection becomes a section, and that is the definition. So let me not say these things, I will not end. So these are very interesting things about injectives, which these things are used to build a counterexample for cancellation of degenerations. But let me not say this now, because maybe we'll not detail the proof of the cancellation part. So, but this is gives an important combinatorial meaning to this arrow A in case of injectives. Yeah. And then path algebras can be seen as tensor algebras and these things, but maybe again, maybe I think I'll just skip this section because we don't have the time. So I'll just skip this section. And the homological properties we are going to need a little bit, but maybe I think I'll just skip this section also, because we will not have the time. Yeah, this one again is now important a little bit. So let me say this is, yeah. So I mean, one can see that in the case of quivers, the way we have described the homomorphisms and isomorphisms between quivers, we need. So a homomorphism between two representations is like n matrices if there are n vertices. Obviously, it can be put as one matrix and so on, but there are n matrices, and so the action becomes of this on RepQ, and yeah, Gx is the stabilizer of this action for X, and these are basically the automorphisms. Okay? And then the tangent space. Now the formula for the tangent space is this. This is an important formula. It is the endomorphisms of V. This is basically the dimension of this big space, right? By the endomorphisms as a representative. This basically becomes the automorphisms this up to dimension. And so that's a tangent space. Okay? But we'll not say these things maybe because we won't have the time. So we come to the main thing. So because we want to get degenerations from algebraic condition. So we want to have one. So this is going to be the classical condition. So when we get degenerations from an purely algebraic condition. Okay. So let's say we have this exact sequence, then the middle term degenerates to the direct sum of the two end terms. So if it's a split exact, then obviously it's algebraically same. I mean, it's a direct sum of the two, but in general, this is like this. So the middle term degenerates to the direct sum of the two end terms. Okay. Proof is not difficult, in fact. The proof of this, and this is for any finite dimensional algebra, and the proof is basically to just write M. So for every generator of the algebra, or for every that alpha I basis that we had, we have a matrix, right? The corresponding action on M gives a matrix, and similarly for M1 and M3. We just pick the right basis. So we pick a vector space basis of M1, you extend it by a basis of M3, that gives a vector space basis of M. With respect to that, when you write the matrix of M alpha I, it becomes like this, where those two are the matrices of M1 and M3. And then one uses a one parameter subgroup conjugation taking limits. You go from M alpha I to M1 directs on M3. Okay? So that proves it. This was the first theorem in degeneration. I think it's due to Artin in 60s. Basically, from algebraic condition, you get degenerations. I don't know if they used this word that time, but this is the first known. Yeah. Okay. So now we are going to have this. So we want to first prove that that condition is necessary. Right? That the geometric thing implies this algebraic condition. So this is necessary. And so we're going to just quickly sketch a proof of this. So if X degenerates to Y, then this algebraic thing happens. So, I mean, how do you prove this? We can leave the intuition. How do you prove this? Well, so we want to prove it for every U. So you fix the U from the very beginning. And then we describe this V. Okay. So this V is basically you take a morphism from U is fixed throughout U to Z, and you take Z. Okay. Now this again becomes a variety. Okay, because a set of morphisms is a variety and so on, and Z. So that again becomes a variety. And then we're going to take a projection of this V onto the second coordinate. So this MD. So basically we want to get these things as fibers and then use a semi-continuity condition. So the pi2 inverse of, so the fiber of any Z is this all homomorphisms from U to Z, and homomorphisms from, and this is a linear variety. And so that's important because then this linear algebra definition and the algebra geometry definition, they become the same for linear variety. And also they're irreducible. That's also going to be important. So now what is it that we're going to use? So given a Z, you take its fiber, and then you take the largest irreducible component, and this is the fiber dimension. Now, because it's irreducible, so it just becomes this, and this is this. And now by the upper semi-continuity condition, we get that this pi inverse of all the Z for, all the Z for which this thing is at least K, this fiber dimension is at least K, this is a closed set. So if X is there, then in the limit point, then the orbit of X is there and the limit point will be there because of this closeness. So that basically proves that this Hom U comma Y dimension will also be at least K, if that is the same for X. So that's is a proof for this. Yeah. So now basically, again, we want to find the converse. When does the converse hold? Now, again, what's the general plan? So the thing is that I'm just trying to say that we're going to break it into two steps. Okay. And first, we're going to find when does this algebraic condition lead to a weaker type of degeneration? And then when does this weaker type of degeneration lead to actual degeneration? And it turns out that in this, by this two-step process, we don't lose anything for certain reasons, but we don't lose anything. We don't lose any algebras. Yeah. So, yeah, so let me just leave it at that. And then we come to the this important definition of virtual degenerations. Okay, so again, it's a loser kind of degeneration is what we are saying. And so if X direct sum A degenerates to Y direct sum A, then we say that X is virtually degenerates to Y. Okay? And again, this is but easy to prove, not difficult, but this is true. Yeah, but the reverse is not true, and that's what we are trying to. That's what the second step is. So maybe again I skip this because so I'll skip this. There's try to put together what work has been done. So skip this thing and some other work, and then now this Oslander-Rayton theory. So yes, so because it's 7:30, so this and then after this we have several other things. So I will just mention that. I will not go into the details of any of these. I've written them here, but I will not go into the details. So, I mean, the key thing I want to show is that there are almost split sequences exist. Okay. So, okay, let me just go through the thing. What should I do? Category of this thing. So maybe I'll just go to the definition of an almost split sequence. This rad, we will, so we will need the rad, So rad, because this we will keep needing in the proof also, this rad thing. So rad V comma W is just a collection of morphisms from V to W, which satisfy this usual definition of rad that is there, okay, right? But then The good thing about rad, so rad is, so first this definition of a section from V to W if this has a left inverse. Similarly, retractions are defined, but the important property which we'll keep using is that if V is indecomposable, then this is all non-sections and so on. And similarly, if W is indecomposable, then this is a set of all non-retractions, two things. And then these other things that the rad and the HOM agree if they are both indecomposable non-isomorphisms. Otherwise, it is the usual commutative algebra definition of rad. So that's just the rad. Irreducible morphisms, just maybe one can take it as just the expected definition, okay? Because we are not going to detail any proofs. So just the expected definition of irreducible if it cannot be factored as G composed H. This condition is there for just to avoid some triviality. So this is square of an ideal. So let me leave these things. Yeah, the definition of the definition is that, so we have this sequence, exact sequence. Is this exact to begin with, but then it is non-split. So non-split is okay. Every non-retraction. So if you have any non-retraction from V to M3, any non-retraction from V to M3 will factor via G. Okay, so there will be a V bar from V to M2. So that V bar composed with G gives you the V, and similarly non-sections, but obviously every non-section from M1 will factor. So these things are there. There are some simplifications and we get a one-sided form, and then finally we get a characterization which we use. But in the end, the result, in the end, what I just want to say is if you have this exact sequence, so in the end, what I want to say, sorry, is that if you start with any M1, indecomposable M1, it has to be indecomposable. It comes from some lemmas, and it is non-injective. You cannot have an injective on the left side and non-split. Then you will get a almost split sequences as we defined. And similarly, if you have M3, which is non-projective, you'll get, and it's unique. So all these uniqueness and these things and F and G are going to be reducible maps. All this is going to come in when we make the AR quiver and so on. So that's, but just that these things exist, and the proof just comes from these characterizations that we give for these things in the finite type case. In the general case, it doesn't come from these characterizations only, it's more existential. Yeah? But so let me leave all these ideas and proofs and so on. Yes, now this is going to be a very important lemma to execute the first step. Okay, so we want to go from homomorphisms to a module to determining the module. Okay, so some things I said, but what I basically want to just say is this, that if dimensions from U to M is given for all indecomposable U and hence for all U, then M is determined up to isomorphism. That is the main claim. And for this, again, Osander-Ratin theory is used. Okay? And basically what we want to use this existence of special exact sequences to say that you can determine the number of copies of U in M, and then Cruz-Smith tells you that that's all you need to know. So we just take a Osander-Ratin sequence starting at U. This is not a trick in the sense that if you take ending at U, one would realize that one then needs dimension M comma U, and so one can. So these are natural things. One takes this and then just homs it. This contravariant functor, we get this. And the right one is, this has to be, I should just say that this should be surjective by definition. And then this co-kernel of F. So if it's a split sequence, then this co-kernel is 0. For almost split sequence, this co-kernel is well understood. It can be described. So what I just want to say is that the dimension of this co-kernel is the number of copies of U in M. That's what I want to say. And again, one uses the properties of rad and things that some things that we didn't mention also to prove this. So this is the important thing. And so basically this K, which is the number of copies of U in M, is this co-kernel of F. But this is just from the dimension things. These three quantities in the end, we know dimensions from, okay, so this bracket just means dimension of HOM from tau inverse U to M. That these three things are known, and therefore K is known, and so we are done. Yeah. But I have only proved this when U is non-injective. For the injective case, again, some more work can be done to prove some things, simplifications and some properties, converting it to projective and so on. So, but I'm leaving it there, leaving that. But the point is that only knowing the HOMs from U to M tells you everything. So this is tells you M. So that's going to be useful because when we want to show two things are isomorphic, we just show that the Holmes are same for every U. Some things are needed to deal with the remaining case, but that's fine. Yeah. And yeah, this can also be said as that the degeneration order is a partial order, but not say how. If yeah. So now the construction of the quiver, the Ostrander-Ritten quiver. So the quiver of indecomposables. That is what we want to mention quickly. And obviously the goal is to basically this category of indecomposables, we want to view it as the graph category, some quotient of the graph category, some graph, and that graph is going to be this AR quiver, okay, for the finite type case. Okay? But again, to make this AR quiver, we need to describe a knitting algorithm. And for that, we will need to have some idea of what kind of irreducibles exist, at least to begin with, to begin our process. Ostrander-Ritten theory will do the rest, but to begin the process, we need to know something. So that basically the first thing is that RAD P2P is indecomposable, that's the thing. And only irreducibles to a projective, to an indecomposable projective will come from direct summands of RAD. These things can be proved. And these are all the irreducibles, as I said. But the main thing that will get us started, yeah, is that for path algebras, not for general, for path algebras, irreducible maps from a simple projective, we need to know all irreducible maps from a simple projective to make our AR sequence. That is a necessity. So I didn't say that earlier, but that is a important thing. You need to know all the irreducible maps from something to build that AR sequence. And for simple projectives, which is what we are going to start with, any irreducible map from it is to a projective. And therefore, by above conditions, it is the direct summand of the radical of some projective. So that's really good for us, okay, to get us started. And now the definition. So vertices are going to be the indecomposed modules. And if you have two x and y small, but these are just modules, then the number of arrows we are going to put in is this, because this is the what we get in the Ostrander-Ritten thing. So there's a reason why we put that, but let me, yeah. But in our case, we don't need it. We'll just not have multiple arrows. This finite type. This can be proved. This can be proved, but I am, yeah, this is a statement. There won't be any multiple arrows. Okay, and this is another statement which can be proved. So the former proof, this former statement, I don't know the proof very well, but the later one I know, and this is that for any finite representation type algebra, any morphism can be generated by compositions and addition of these irreducible morphisms, but this only happens for representation finite algebras. And this is the key to getting an easy proof of existence of AR sequences, but it's fine. And okay, another thing which will get us started is that the AR quiver, when you want to make this, you make this AR quiver, which we have defined of some finite representation of algebra A, then if you take the subgraph, the induced subgraph of the projective vertices, then that is just Q op. And that one can, that from the examples of irreducibles one I gave, that can be deduced. Okay? So now we want to just quickly, so maybe I'll not say this algorithm too much detail, but just the point is that we start with all the simple projectives, why we start there, and then we make all the successes from the simple projectives too. And we need to make all the projectives also because certain reason. And then we make all the predecessors which we can. Okay? Now, every other indecomposable, yeah, because we have taken care of the projectives, will be the end of some AR quiver. Some Ostrander-Ritten sequence, right? And so they can be gotten by a knitting. They can be gotten from the previous ones if you know all the irreducibles from the previous ones. So that is the thing. So what we do is, for example, you start with certain projective for which all the successes are known. Then you know that you will get, when you knit it, you will get an AR. You get an AR sequence, and you get that new indecomposable, and every indecomposable can be gotten in this way inductively. Obviously, this needs a proof. Some things are still there, but basically what we need to ensure is that when a new vertex is added, you are able to find all its successes. But then all its successes can be found if for every predecessor, which are already known because you get this by knitting. So all its predecessors are known. For every predecessor, all successes must be known. Then you can find a successor of this also. Again, that's from this Ostrander-Ritten sequences. So but this can be done. So it's fine. We are going to do it for a simple case. Okay. First for the standard orientation, but then we're going to generalize this for general orientations because that's what we will prove the cancellation of degenerations for. So when we execute the first step of drawing all the projectives, then this is what we get in the opposite arrows in the opposite order. And this is the scheme that we're going to use to write the AR quiver. The upward arrows are vertically upwards and this first step. But the second step, okay, this is something, well, let me just leave that. Yeah, these are the non-injectives. This turns out to be injective. Again, it can be proved easily from the other. Well, yeah. The point is that we compute all the successes of what we have so far. And that can be done starting from the lowest one. It's safe, then you would know that you get all the successes. And how do we know that this is the only other successor of P4? Because for any successor, you would have an AR sequence ending there. And so when you go back, because of the uniqueness of the AR sequences, because only have one predecessor, you cannot have two successors. Otherwise, you would need. So yeah, those things can be proved. And so we get all the successes. And then now, because you know that, for example, for P2, you have all the successes known, you can knit. And so all the successes are known, so you can knit, and then you can continue. And we get this nice here. Okay? On the right boundary, we get all the injectives. And everything about the injectives is the same because of the duality. Okay? Only that we draw it in the opposite way, and the arrows are in 45 degree rotation. So basically, so the shape of the left, in this case, this is the AR quiver. Okay? But then we can generalize this. So for the arbitrary orientation, so first of all, one should notice that for any orientation you take, the number of indecomposables is not going to change, because the number of indecomposables is characterized by some roots of a quadratic form, right? So it's positive roots of a quadratic form. So those things are not going to change. Okay. So that's a good thing, that the number of vertices are not going to change. And even what is to be, let's just say number of vertices is not going to change. That's all we know so far. Yeah. Let's take an example. If you take this quiver, arrow from 1 to 2, but from 3 to 2. And so for this, again, just following the case of the, following the rule for the projectives, the irreducible morphisms from and to projectives, we get this thing. Again, the scheme is that your downward arrow is like is southeast, so it becomes this. Obviously, this below the bottommost one is P5, and that's the scheme we follow. We get this. Now the right boundary of the injectives will be the same. It'll have the same shape, but because it's just 45 degree, and because we are the vertical order is the opposite, so the right boundary, but it's understood. And now the gap, right, is also understood because you know the same number of vertices. And so my point is that the relative position of, let's say, P1 and the relative position of P5 and I5, or P1 and I1 is not going to change. But the relative position is easy to calculate in the standard, under the standard thing. And so in general, you can calculate. So this is going to be the formula. If Pk is I comma j, then Ik is going to be I plus. So it can be calculated. That's the point. And then you can just fill the meshes in between. And that's your AR quiver. So we know the AR quiver for any orientation. That is, yeah, that's the thing. Now we execute step 1. So yeah, so now we execute step 1. So what is step 1? We want to go from the Hom order, the algebraic condition, to the, we want to finally go to degeneration, but we go to virtual degeneration. Okay? So we make this assumption, yeah, because, well, we know that this is the same as, wait, no, sorry, this is the assumption. This is the Hom order that is given. So this is the assumption. Again, this just means a dimension of Hom u comma x. Okay. Now the claim is that in finite representation type algebras, x direct sum A degenerates to y direct sum A, means x virtually degenerates to y. So I will again not complete the proof, but just outline the proof. And yeah, let's see. Yeah. So well, the only way we know how to show that something degenerates something is via this, so far was via this exact sequence, right? So suppose we had this exact sequence, and so then we get that B degenerates to A direct sum C. We want to get that X direct sum A or something, some A, right? So then we get this, just you can add X on both sides. But then you would want this X direct sum A to be isomorphic to Y direct sum B, because that's how you're going to get X direct sum B is degenerate to Y direct sum B. And so that will be, so this is what we want. So now we have reduced this to just making an exact sequence, so that X direct sum A direct sum C degenerates to y, is isomorphic to y direct sum c. That's what, so this is the exact sequence we are going to make. And the claim is it exists. And again, we are going to use existence of, so this is not going to be an Ostrander-Rayton sequence, but we're going to use Ostrander-Rayton sequences to build this. So that's the general thing about Ostrander-Rayton sequences are sort of minimal in some sense, that they generate all relations in the, among the homomorphisms in finite type case. And here they are going to be used to build this, exact sequence that we need so that this isomorphism condition holds. Okay? And so again, one can just work a little bit backwards. So this condition that we have, that x direct sum a direct sum c is isomorphic to y direct sum b, we want to see it in terms of Holmes, because as we have proved earlier, this is equivalent to saying this for all u. And then just some working out tells you that this delta, now this quantity which is denoted by delta, this is delta u of an exact sequence. Okay. It is basically just the dimension of the co-kernel of the Hom u applied to that exact sequence. That is equal to this. Now this is the delta x comma y u. This is the delta x comma y. It is different. So this quantity will keep appearing, this in admissibility and so on, which we will describe later. We want this for all u. Okay. But then we know that if you have an AR sequence like this, from A to B to C, then C is indecomposable. If C is indecomposable, then what is the delta sigma? Basically, the co-kernel gives you the number of direct sum copies of U in C. That's either going to be 1 if it is isomorphic or 0 if not. So this tells us what exact sequence we should make. So the exact sequence we should make, should have delta U copies. The C should have delta U copies of U. Right? Delta U copies of U. And so what we're going to do is for each indecomposable U, we are going to take delta U copies of the AR sequence ending at U. Okay. And we will do this for all U, and we can, because it's representation finite, and we're going to add those exact sequences, just add in the natural way, not combining the maps. And so just add the sequences simple way. And basically this is the exact sequence. It can be easily checked that this indeed works. Okay. It's almost from what we have said, but one can check it. And yeah, so from the AR sequences, from exploring this condition in terms of Holmes, we know what sequence how we should make the sequence. And the proof can be just checked from here. Okay. So again, this sequence is just, we take the AR, so for every U, we take the AR sequence that ends at U, we take delta U copies of that, so that when you apply the Hom U, you recover that delta U, and you add those exact sequences. So that is the thing. And so that's it. This is mostly, again, this is almost the proof. Again, the case for projectives is remaining, because we cannot do this when U is a projective. But again, that can be done, but let me not do it. Let me not say the details now. Yeah. It's easy. So let's come to step 2. So so let's come to step 2. So in step 2, we have this fact that degenerations cannot always be cancelled. So that's the first thing. So let me completely skip this example and how and example and what's the idea and proof and so on. Let me just come to again, but to again deal with this problem of cancellation of degenerations, we are going to make 2 assumptions. Okay. And these are valid assumptions. That number 1 is that to show that cancellation happens in A mod I, we will just show that cancellation happens in A, and that implies. So we will not do it for admissible quotients, but we will just do it for the path algebras. And the fact that this can be done is easy to prove, but yeah. And another thing is that, again, these things can be proved against some Ostrander-Rayton theory. What we are going to assume is that this degeneration from virtual degeneration from X to Y is irreducible. So step 2 means that we have a degeneration from X to Y, and we want to get we have a virtual degeneration from X to Y, sorry. We want to get a degeneration. We're going to assume that this virtual degeneration from X to Y is irreducible. And again, this can be assumed. And irreducible just means that you cannot put in a non-trivial thing in between. Otherwise, it will be isomorphic to 1. Why this can be done? Let me skip it for now, because we will not have the time. But there's a... So yeah, now this is the step 2. So we have made, and also we'll assume that there are no common direct summas. Now that can also be proved that it can be done. But let me... So yeah, so we want to prove degeneration. So we want to prove, so again, the standard thing we'll do is you'll show that there's some sort of a sequence like this, so that X degenerates to the 2 n terms. Okay, and this is true but then so that the two n terms direct sum is equal to y. That is what we are going to prove. Okay. But again, we will need some more notions. So should I, yeah, so this is, so what we are going to, so there is again this notion of mesh category, but let me just go to the absolutely essential thing. These are all needed to understand thing, but the final thing that I want to just say is we are going to make a category called the mesh category. And the mesh category is just that AR quiver of your algebra that you started with, the AR quiver. Okay. And we are, so what are going to be the hom x comma y? So they are going to just be the formal, vector space of all paths from x to y, but then you're going to quotient it by all the relations that you can get from the Ostrander-Ruyten sequences. Okay, so that's basically quotienting by all the meshes, but all, so basically, so if you have this x and y, and you have this one path simple and let's say another simple path, right? So formal linear combination would mean that you have this path and all its combinations, yeah. But if this is an AR sequence, then this path plus this path is 0, and so you quotient by that relation, simply put. So that's, we are going to quotient by that. Obviously, those relations are there in the hom category because the exact sequence, so it's 0. Those relations are there. But then again, this is a slightly non-trivial fact as I understand it, is that these are all the relations. And so this mesh category that you get by this quotienting of this graph category by the Ostrander-Ruyten relations is equivalent to the indecomposable. And it's good enough for us because we have reduced the problem to sort of just proving exact sequences, and they don't change under this equivalence of categories. So we will work with a mesh category because it's much more combinatorial. Okay, so yeah, so again, there is a general plan how to go from virtual degeneration to degeneration, which works for several cases, not just what we are going to detail the proof of, but and how it comes is skipping is some, but it comes in a natural way as I've tried to decipher it. But the point is, in the end, this is what we are going to show. We are going to show that there is an x comma y admissible sequence. So I mean, initially we wanted to show this. 1 minute, yeah. So we are going to show that there is an exact sequence like this. So this y1 to b to y2, so that this n terms are direct summands. Initially, we said that you would have to make the n terms direct sum, but that condition can be removed. Okay, the n terms are direct summands, and also this delta sigma of this sequence for each u is not more than delta sigma of sorry, it's not more than delta u, delta x comma yu. Okay. So that delta, so the delta of the sequence is not more than that, and that's the admissibility condition, which comes in a natural way if one works it out. But yeah, so that's what we want to show, that we want to make an exact sequence in which the n terms are direct summands of y, and this is admissible. So this delta of the sequence is not more than delta x comma y for every u, so that as a function is dominated. So that's all we are going to. And then we would like to first start this exact sequence. Okay, and mentioning this separately because this start of this exact sequence, the way we do, works for general. So in the other cases, or some other cases also. So how do we do? So I mean, starting the exact sequence which we want to make to get the degeneration would mean that the left hand term you would want to ensure that it's a direct summand. So how do you ensure? It is like this. So you pick a, such a will exist so that the delta x comma y of a is positive. This is just the difference between the dimensions from u to a and from a to x, a to y, and a to x. It's the difference of that. We know that it cannot be negative because of the virtual degeneration. We have proved that thing. But for something is going to be strictly positive, and that is, we're going to take that. Again, that is true that it's going to be strictly positive for something, because if it's 0, then it becomes isomorphic, so x and y become isomorphic. Okay, if it happens for all a. But then we're going to also going to pick an a which is minimal, in a sense of in the AR quiver, it is minimal. And again, that can be done. A cyclicity of the AR quiver can be established, and so that is fine. I mean, at least for the AN case, we have seen it's a cyclic, I mean, in the oriented sense. So once you do this, then the not a, but this tau a And the tau A is just the standard writing sequence the start of the standard writing sequence, which ends at A. This is the direct summand of phi. Again, the proof is not difficult, but I'm skipping the detail of this, because there's no new idea in this. This is similar to applying Hom and computing some things and delta A. So we know how to start our exact sequence. We should start it from tau A, okay. And this will be a guide to what vertices in the exact in the standard writing quiver, which is we should focus on. And then the end term also one needs to decide, so that one gets the admissibility and the fact that the end term is also a direct summand of phi. So we will need both the things. So now the important things, okay. So again, I've already mentioned this, but just one more example is this. For this thing, this will be the AR quiver. There is one mistake here. So this particular edge, this should be in the upward direction, okay, because this is downward direction, so this should be upward direction. That again can be proved, but this is should be, that's a small error, yeah. So this is the ascended by delta, now by gamma. Now it can be just it can be said in certain language of subtranslation quivers and so on, but let me skip this because it's not absolutely essential. Now the mesh homotopies. And what are the mesh homotopies for? Well, basically we see that, I mean, every mesh. So this is the mesh that looking at. Every mesh, has size 2. And so if this is like F1 G1 and this is F2 G2, then they have this is right. So basically, when you go from the upper part of a mesh to lower part of a mesh, then the actual map in the mesh category and hence in the end category is a negative of it, right? So that we are going to exploit by this definition, okay? And we are just going to say that if you have any path from X to Y, one path and another path from X to Y, and if you can get from if you can get from one path to the other by making this switching of these meshes, yeah, then you're going to call them homotopic. And then you take the equivalence relation generated by, because there could be more things get related, and by these, and these are called mesh homotopies. And then basically any two homotopic paths are the same up to sign, because that's how they are generated. And signs, exact sign can also be described. And but another fact is that any two paths are homotopic in this graph. I mean, with the same endpoints, they are homotopic. And so what this means is that this gamma represents that it's a mesh category, Hom X comma Y in the mesh category. This is just one dimensional. And so the same is true in the actual end category also. So this is one dimensional in this AR quiver for this AN or any orientation. So that's the important thing. But obviously some of these paths could be 0. For example, if you take this path from P1 to I6, which goes down and up, I mean, this path is 0, right? Because this is just composition is 0, right? So it will be 0 in the mesh category also. That's the equivalence we have already shown. But in general, when is a path 0? It could be non-trivial without this. I mean, it could be messy to say this without the mesh homotopy thing, but in the language of mesh homotopies, I mean, any path from X to Y, is basically 0, which means that the delta, this gamma S comma Y is 0, because everything is homotopic, and so it becomes 0 dimensional if it is homotopic to a path that passes through the top border or the bottom border. So, and that's if and only if thing. And this is again going to be important because we're going to simplify a lot of the arguments in cases. So 0 dimensional if and only if that happens. And then that basically we say in terms of an essential path and non. So non-essential paths will be those paths which are homotopic to paths that factor to the top or the bottom border. And now the key combinatorial model, which will help us to capture all maps from starting from something, all non-trivial maps, to capture that to what kind of things we should look at. And for that, because that's what we want to do, we want to make an exact sequence with certain properties. And so the definition is, so, I mean, you look at any vertex A and any vertex C, let's say, so any vertex A and any vertex C, you look at all the Ds so that there is a non-trivial map from A to D and then from D to C. Okay. So basically the non-essential path, you could say in that language, from A to D and D to C. And for example, if you pick the A and the C that I have, if you pick the A and the C that I have picked, why did I pick this? Sorry, one second. Yeah, so let's see. So if you pick the A and the C that I have picked, then RAC is empty because there is no essential path from A to C. Because if you look at one of the paths from A to C, then it just goes down, up and down. but then that's a zero path because the final thing is to the bottom border. So for this thing, RAC is empty. So it could be empty. But it has a very clean description. If you take RAC, if it's non-empty, then it is just this just obvious parallelogram. Okay, and even when it's empty, you would know the parallelogram kind of has to go below where it can, and so it's empty. Yeah, and again we're going to assume A is not projective. It's the reason why we assume that it's, but yeah. And I mean, again, this is an important thing that RAC, this rectangle cannot hit both the bottom and the top and the bottom border when A is not projective. So when basically when you don't pick A on this border, then so when you don't pick it on the border, then you pick any two vertices. You could pick it on the right border, but not on the left border. Then the RAC will not touch both. And it's important for us for it to not touch both the upper and lower border. Okay, it can be easily proved from this graph is there. So and we know all the coordinates, and so it can be proved in any case. Yeah. So we want to describe the path from tau A. So pick an A, but we want to describe the path from tau A to C because we know we should start our exact sequence from tau A, and so that's what we do. And for that, to describe that path, we make a new definition BAC. But the BAC, forgetting the definition, we can just look at the picture, is like this. So if you take A and C, then you get this sort of a rectangle, but then there is just this B, which is just northwest to it and has an arrow to it. That B is our BAC, and the other option is from the just below the rectangle to it. And there is a definition, but maybe I can skip the definition. This is what those two things are, the BAC. What that does, it will give a unique path from tau A, because the tau A, if this is the A, then tau A is just going to be here, and it gives a unique path from, it helps you to describe a unique path from tau A to C, and also both. Obviously, I mean, if the rectangle touches the bottom border, then the bottom B would not be there, but it won't touch both, so at least one of them will be there, so there will be some path. That's important for us. So for example, in this picture, this is going to be our B, if that's, and the bottom B is not there. Yeah. So now construction of the exact sequence, how would we make the exact sequence? Just the natural way. We're going to start from tau A, and so basically from tau A, we can see that you can go to both the B's in the natural way. That path, which is a map in the mesh category, and it can be interpreted as a map in the ind category. But let me just not say in the ind category anymore. From tau A to both the B's, you can describe this natural path. So you get two paths. From tau A, you get two paths, and that gives you that they will land up in this indecomposable. And then basically you extend those paths to C in the natural way. You put some signs, they are there for a certain simple, they are there, so they are easy to, one can work the signs out and why they are there later on. So this is the exact sequence. This is not going to be the exact sequence, but this is the exact sequence from A to C, or from tau A to C. And so basically for every rectangle, for every A comma C, we get this thing, this exact sequence. Now, why is this exact? So there are, again, steps in this. So yeah, what we are going to use is, we are going to use the home characterization, because we are, yeah, so maybe I can say the more details if needed, but right now I'll just say not too many details. Okay, so we are just going to use the home characterization, and in particular the top one we are just going to prove. Okay, so that basically comes down to this. So what we essentially just want to prove is that, I mean, given any x, right, the x could be here, from x to tau A, if you have a map, right? If you have a map from x to tau A, you could use it to get a map from x to B, and then again get a map from x to C finally, right? Using those from B to C maps, right? We want to show this is an exact sequence. So the first thing is that we want to show that this is an injective. This is injective. And for that, we just use some things from injective envelopes. And again, some properties of the graph, okay? So yeah, let me say this one. So we take the tau A. So you take tau A and you take an injective envelope of tau A. So direct sum of injectives. So those JKs are on the right border. That is important. Okay. So the right border is an injective map. Okay. Now, if you apply X of this, then what does it mean? Basically X to tau A, and then you just take the maps from tau A to JK to get map from X to JK. But it's on the right border. That's important. Right boundary. So I mean, what that just means is that if you have a map from tau A to JK, you take any map from tau A to something which is on the right border, okay, right border, then it will factor through one of the B's, or it will be homotopic to something factoring through one of the B's. That can be proved from the graph. Okay, if not the upper one, from the lower one, it would factor. So that is important. That would mean that this map that we have, this xik, this sum of ik's, this factorizes through B. And that establishes the injectivity of what we need, the x to tau A to x to B, because of this is injective by injective envelopes. So again, just a small property of from the graph that we can see, we are able to establish this. So that is first thing. And then, I mean, then the other things are there. One can show that. So there are two things now. The fact that it's a complex can be shown, and then the other fact that if you take any path from x to B, which when extended to a path, get a path from x to C becomes 0. I mean, there'll be a pair of paths here potentially. Then that factors through tau A. Now again, that is split into two cases. There are some details. So maybe I will skip that, but it can be proved from it, but the arguments a little there. So maybe I'll skip this because there are a few more things that I have to say. So basically the exactness, I am assuming. Now we know that all these sequences that we have made, they're all exact. Good. Now we want to get admissibility. Okay. So we should investigate the delta of these sequences that we have made. But then again, because of the dimension of the maps and the arguments that we have given, if you pick any point U inside or on or inside the rectangle RAC, then this delta sigma of that is 1. I mean, what that is basically saying is that there is a non-trivial co-kernel. And what that is basically saying, if you have a U is inside, and if you want to go from U to C, right? Then that path from U to C can never be factored through a path from some B, which is outside the rectangle. That is impossible from the arrows and so on. And so you do get a co-kernel. And in the other case, you don't. That can also be proved. That this needs some, but it can be proved. And so point is that this is a very simple delta to this. To these exact sequences have a very simple delta. Okay. And so now admissibility, in the idea, admissibility just means, so if you want this sigma AC, that this exact sequence to be admissible, that basically means that the corresponding rectangle, there's a rectangle corresponding to the sigma AC. That for that rectangle, for every point inside that rectangle, the delta should be at least 1. Otherwise, it will not dominate this delta sigma at U, right? So it should be at least 1. So that is the condition. And this is a very important condition. It will allow us to take maximal RACs starting from any A, maximum, and so on. So it's an important admissibility condition. So we have the admissibility condition. Now we want to get a sufficient condition so that the right part is also a direct summand, right? So that the C is a direct summand. Okay? So let me just mention the condition. For that also, we need to make a few definitions, but let me just mention the final condition. Okay, some things, but there's another definition. It's analogous to the BAC we had earlier, but it's not the same. What it is, just from a picture, it is just, if you have the AC, then this one and just this southeast. But it could even be empty. None of them could exist. It's possible that none of them exist. If C is injective, it is possible. It doesn't mean that if C is injective, then it's empty, that those B primes won't exist, but it's possible. But it is not a problem for us. In fact, it's better if that's empty. There's no problem. So that's fine. In the earlier case, it was important that it is non-empty, but the right analog could be empty and it's not a problem. And the map that we make is just, so basically from A to C, we want to get the path just in the natural way. Earlier we have from tau A, but now from A to C, and it's just natural. Now using this and some other notions, delta prime associated to it, which has a similar property, one can finally prove this condition. That if, so we know what these B primes are, right? The B primes are this corresponding to every rectangle, we have these two B primes. Okay. Now we just want a sufficient condition that this RAC, so not necessarily that C is a direct summand of Y, but RAC contains a direct summand of Y. That is enough for us because subrectangles are also going to be admissible if the rectangle is admissible because of the characterization we had. And so the condition is that if this delta x comma y of A is at least delta x comma y of B prime over the two B primes or 1 or potentially 0, better, no problem, then RAC contains a direct summand of Y. So we just need the sufficient condition. And so this is a proof is, again, I'm not told the proof, but I could if needed. So this is, so this sufficient condition we're going to use. Now we're going to, now it's done. Just the last step we are going to execute. Okay, is the existence of the admissible. So all after all this, the existence just becomes simple. So what we want is an admissible rectangle, left and right in terms of tau A and C, both should be direct summands. Tau A is taken care of, admissibility is C. So, but let's do this a little slowly. So what we do is we pick a minimal A so that the delta A is positive. This takes care that tau A would be direct summand of Y. Okay? We need the right one, that is a C, so, so that the RAC is admissible. That's important. And the second thing is the C is the direct summand of Y. Or I'm sorry, we cannot put such a strong condition, just that it contains a direct summand of Y. That would be enough, because wherever that direct summand is, you restrict the rectangle to that part. That's also admissible by our characterization. So that is fine. Now this is the very last thing. So we have this. Now, obviously, we're going to start from A. We're not going to change that A. We're going to start from A because the left-hand term is taken care of, so naturally it will not change. And naturally, we pick the maximal admissible rectangle that you can starting from A. So why is there an admissible rectangle starting from A? Because just A comma A itself is admissible because delta A is positive. So it's admissible. But we take the maximal, because that's the best short tool. So we take the maximal admissible rectangle starting from A. We make a maximal, obviously. So, and let the other endpoint be D. So that's RAD. Okay. Now, because this is admissible, so if we look at this lower diagram, let's say this. So why did I mark this? So this one is not A prime, it is just A. So this is your RAD. Okay. This is maximal. What does that mean? It means now the possible upward arrows from here and the possible southeast arrow, these are the possibilities of extending, right? Upward or, but because this is a maximal admissible rectangle, it means that one of these pink for, I'm sorry, very sorry, one second. Sorry. Because this is a maximal rectangle, because this RAT is a maximal admissible rectangle, at least one of those pink, for at least one of those pink dots, right, the delta should be 0. If it was non-zero, it means it would be positive, then you could extend the rectangle upwards. Okay? So one of them has to be 0. Let's say that this orange one that I've marked, this one, I mean this corresponding pink one is, for that is 0. And similarly, one of the green ones has to be, the delta has to be 0, otherwise you could extend it. Okay. So now this tells us what we should do, because I mean, this pink one for which the delta B is 0, that should become the B prime. And again, this should also become the B prime for my admissible rectangle, because if the delta B prime is 0, then that sufficient condition of being a direct summand is automatically satisfied, right? And so that's what you should know. If those pink and green don't exist, then we have no problem. Then it means that there is no, those things are not there. And so then it will automatically already contain a direct summand. So then that's not a problem. Yeah. So, but if there are these things, then we can work it and get this A prime. Yeah. And once you pick this A prime, then for R A prime D, the corresponding, the pink and the green ones, just to this thing, for them the delta of B prime, those are the B primes, that is 0. And so delta A, this should be A prime. That delta A prime is certainly greater than that, because that's 0. And so that means that this RA prime D contains a direct summand of Y. Okay. And RA prime D is already admissible because of our condition, and it contains a direct summand of Y. So it's admissible, contains a direct summand of Y, and this A prime that we have, for this also the delta is positive, right? So there will be, no, so there is, so one second. So there is a certain I think here, which I want to, so it's an admissible rectangle, right? And D is a direct summand of Y. Right? It's an admissible rectangle. It contains a direct summand of Y. Those two things are taken care of. But what I have to also say is that tau of A prime is a direct summand of X. I need to say that tau of A prime is going to be a direct summand of X. Yeah, so the delta of A prime is positive. Yeah, but the tau of A prime, but that doesn't imply that the tau of A prime is a direct summand of Y. No, so that doesn't imply, yeah, that does not imply. The A prime has to be minimal with respect to that property for us to get that. So so this was the very last thing, and I think I have missed that. 1 second. So this A prime, yeah, I just need to ensure that this tau of A prime is a direct summand of Y. So for that, the delta A prime must be positive, but A prime should be minimal with respect to that property. And so for anything below the delta should not be positive. 1 minute. So how is that going to work? Yeah, so it needs to be minimal with respect to that property. So with respect to, so I mean, there is no arrow from this A. So sorry, this is just A. So this is just A. Yeah, and there is no arrow from here, but I need to also say that this is minimal with respect to the property that delta A prime is positive. Otherwise, this will not be a direct summand of, yeah, because now I'm starting my exact sequence from tau A. So somewhere here. So this, this is just the very last line of the proof, but so why cannot delta of this be positive? It is positive. Yeah, so I think I missed to check this somehow.
Okay, I'm completely lost, honestly. So, I don't know, Upendra.
Yeah, so actually, what I wanted to say is that I would like to have a copy of this written presentation, so to sort of go over once again.
Yeah. So I'm hoping the next 1.5 months I will be able to read what he's done.
Okay. So but this is the yeah. Okay, this was the very last line. So the okay. Yeah. So yes, so that is the end of the proof, modulo the fact that I am unable to say why I'm unable to say why tau of A prime would now be a direct summand of Y. So somehow I have missed that, and because A is a direct summand, tau of A is a direct summand of Y, but tau of A prime did not be. That is just this final small thing which I think I'll just give me 1 second. So now I missed it. Yeah, because we do need that. Yeah, or maybe, so I think, yes, I think one can ensure that if one takes the last, so there will be several things for which this is 0, for which the pink dots for which the delta is 0, and here one takes the smallest. So one takes the last of these and one takes the last of this, yeah, then one can ensure that the A that you get, its tau A is a direct summand of I. So again, one has to give another condition on the extremality. Yeah, that seems to be the thing. Yeah. So that is the end of the presentation.
Indra, you have any comments?
No. So I